So if you haven't submitted an abstract, technically the abstract deadline has passed, but the form is still open. So if you haven't, I encourage you to submit. You can either do that using copying the QR code or going to the AQC website. And for those who are interested, the registration will open sort of in the first week of April. Okay, so let me begin by sort of motivating the computational problem that we're going to try to solve. And I know that for this audience, you don't really need this motivation, but let me do it anyway. So the goal for today is going to be approximating ground states of quantum Hamiltonians. And the reason we're interested in this problem is that, of course, it appears in various guises across different areas of the physical sciences, right? So here I just give some examples, right? So for example, in quantum chemistry, people talk about the electron structure problem. And for us, let's say we're interested in quantum computing, the Fumoko example keeps popping up. So what is Fumoko? Fumoko is the primary cofactor of nitrogenase, and nitrogenase is basically the enzyme that bacteria in nature use for nitrogen fixation. And so for us, let's say as humans, if we want to come up with new enzymes that do nitrogen fixation even better than the way we currently do it, right? One approach would be to try to better understand Fumoko. And to do that, we would want to begin with finding its ground state and studying its properties. But moving away from quantum chemistry, right, in condensed matter, right, we're interested in studying lattice models, for example. And a good example of that would be, for example, the Fermi-Hubbard model. We'd want to understand the ground state of the Fermi-Hubbard model as we tune its parameters, or let's say cousins of the Fermi-Hubbard model. And why would we want to do that? Well, because let's say, some people think that high TC superconductivity is related to the Fermi-Hubbard model. So if we want to sort of understand high TC superconductivity and how it comes about, being able to study the ground state of the Fermi-Hubbard model might be interesting. And going, to an extreme, we can even go to high energy physics. We might be interested in studying, the bound states of quarks, right? So for example, we could ask, are there stable bound states of 6 quarks, which are sometimes called hexaquark? So why might you be interested in that, right? So at least for a while, people were talking about, and maybe they still are, about studying or asking whether there is a stable bound state of up, down, strange quarks, and whether that could be a candidate for dark matter, right? So all of these are, problems that you can think of as being, the way you would solve them, at least, or to begin to solve them, you would want to solve for the ground state of a quantum Hamiltonian. Now, one thing I want to make clear, at least for this talk, even though I'm not saying it's not interesting, but in this talk, we will not be considering like classical optimization or, like solving for the ground state of spin glasses or Ising models, right? And that's not to say that it's not interesting. It's only that, usually these problems are described by classical Hamiltonians, and that's not at least what we're going to consider today. So, it sounds like solving for the ground state of a quantum Hamiltonian is a natural problem you would want to solve on a quantum computer. But we know that, in the worst case, even a quantum computer should not be able to solve all k-local Hamiltonian problems, right? So, even in the worst case, we shouldn't expect a quantum computer to be able to solve these problems efficiently. But you might ask, well, we're not interested in solving all k-local Hamiltonians. We're only interested in solving, physically relevant Hamiltonians. So maybe the ground states of physically relevant Hamiltonians are easier to find, right? And here usually the words that people will say is that nature seems to find them, so why can't a quantum computer, right? But you might also say, well, nature is messy, and nature may not actually find ground states. Maybe it finds sort of these metastable states with very long-lived excited states. So maybe it's enough to find these low-lying excited states for our practical purposes of understanding physical phenomena. And maybe for that problem, a quantum computer can, let's say, find those excited states more efficiently. But what worries me is that maybe if you've now made the problem easier for your quantum computer, maybe you've also made it easier for your classical algorithm, right? And so, the motivation for this talk is going to be that, when the day comes when, the blue team, right, which is, let's say, our quantum information community, declares that we've solved a practical quantum Hamiltonian problem far more efficiently than we could have classically, us on the red team, we want to make sure that we can say, yes, we've tried we've tried our best to develop the best classical algorithms, and indeed we cannot beat the quantum computer, right? So I feel like it's part of our job in the quantum information community to also continue pushing on the classical algorithms front to really make sure that the day our quantum computers get good enough to solve these problems, they've really beaten the best classical algorithms out there. So what might we want from a good, let's say, classical algorithm, right? So these are just my sort of requirements. I would say that the first thing I want is for the classical algorithm to have an efficient representation of the quantum state, right? So, we know that naively, we could always choose to represent the quantum state in terms of if it's a system of n qubits, in terms of a vector with 2 to the n complex numbers. Well, we definitely don't want to do that, right? Because we don't want to carry this exponentially large vector during our computation. And of course, we want to have some kind of efficient way of updating this representation, because we could have an efficient representation, but if it takes us extremely long or exponentially long to update it, that's not practical either. Okay, so just to give you a let's say a flavor of this of algorithms you might know, right? So for example, we can use quantum Monte Carlo methods to study stochastic Hamiltonians, right? So in these quantum Monte Carlo methods, usually what we do is we have, let's say, our partition function, and we choose to expand it, or we expand it in a particular way, such that this partition function can now be expressed as a sum of weights, or let's say terms that we interpret as weights of classical configurations of some classical system. So our quantum system could have been a system of n qubits, but now it could be that it's now a classical system of n prime classical spins. And how do we use this? Well, we could then develop Monte Carlo or Markov chain Monte Carlo techniques or simulations to basically sample from the probability distribution defined by these weights. And because we're starting with stochastic Hamiltonians, these weights are guaranteed to be positive, and this works out perfectly. Now, one thing, so quantum Monte Carlo is a workhorse method. It's used across disciplines. One thing I want to caution is that just because you have a stochastic Hamiltonian where you have like a nice efficient representation, and you have, let's say, an efficient update scheme in terms of your Markov chain Monte Carlo simulation, it doesn't mean that you've solved your problem efficiently, right? It could happen that even though you satisfy these two conditions, you still need exponentially long time for, let's say, your simulation to equilibrate, right? And a classic example of this is, quantum spin glasses. You can have quantum spin glasses described by stochastic Hamiltonians, but they take, exponentially long times to equilibrate. But for us, another big problem of quantum Monte Carlo is the fact that we're restricted to stochastic Hamiltonians, right? And as soon as you relax this condition and start considering non-stochastic Hamiltonians, what happens is that it becomes very difficult, if not impossible, to find a expansion where all of these weights are positive, right? So what happens is that with non-stochastic Hamiltonians, these weights can be negative or complex. And this is what we refer to as the sign problem. And when we have the sign problem, you can't just straightforwardly apply your Markov chain or Markov chain Monte Carlo simulations because these weights are negative. and you can't interpret them as unnormalized probabilities. Now, this doesn't mean that you can't use quantum Monte Carlo methods with sign problematic problems. You can, but there's a cost. It turns out that what quite often happens is that you end up requiring an exponentially large number of samples to get good estimates of your expectation values, and so this becomes inefficient. Well, so you might say, well, okay, there are other tools out there, and one tool that physicists, for example, like to use are tensor networks to represent quantum states. So sort of maybe the most famous example are these one-dimensional tensor network states called matrix product states. And usually they're given this kind of diagrammatic representation. And the way to think of it is that the quantum state is basically is represented with this product of this rank 2 tensor times this rank 3 tensor, rank 3, rank 3, rank 2. And basically the size of your representation depends on how the range that you allow these indices to run over, which is sometimes called the bond dimension. So with these representations, you then have algorithms like the density matrix renormalization group algorithm, or DMRG for short, which are variational algorithms that update the representation, and let's say to find the ground state, and they turn out to be very, very effective for finding the ground state of gapped 1D systems. But where does it run into trouble? When you use, let's say, an MPS state to describe a 2-dimensional system, and you use DMRG, then that's where it starts not working very well. And then you might say, well, why restrict yourself to a 1D tensor network? Go to a 2D tensor network like PEPS, but then DMRG still doesn't work very well. So really, there's an issue of moving up in dimensions with these states. Now, in exactly sort of analogous way or thing that we saw with the quantum Monte Carlo, just because you have an efficient representation doesn't always mean that you're going to get to the ground state efficiently, right? So that's always something to keep in mind. So with these two sort of, let's say, problems, which is the sign problem for QMC and maybe this sensitivity to the underlying geometry of your Hamiltonian, this is the primary reason that I got attracted to using artificial neural networks to represent quantum states, because it seems like they circumvent these two problems, right? So first, because this is an area that's been studied a lot in machine learning and artificial intelligence, there are a lot of different neural network architectures that you can choose from, and you can update these architectures or the parameters of these architectures in a way that doesn't care about what the underlying Hamiltonian looks like, right? So it's not like you have to change the algorithm depending on what your Hamiltonian looks like, whether it's 1D or 2D. And then you can also use sort of good, efficient variational Monte Carlo algorithms to update the neural network, and these Monte Carlo methods don't suffer from a sign problem, right? So it seems like using artificial neural networks sort of circumvents at least the obvious problems that I described earlier. So just some examples of these neural networks that you'll hear about if you read about this topic in the literature, right? So it started with restricted Boltzmann machines, and this is like a picture of what an RBM looks like. And this is what I will focus on in my talk, and I will explain them in more detail next. But there are also these convolutional neural networks, or CNNs, and this is kind of a diagrammatic picture of that. There are recurrent neural networks, there are group convolutional neural networks, and I'm sure there are many, many other networks that people have studied for this problem. So let's discuss what an RBM is, and I'll try to give you sort of an intuition for them. So an RBM, you really should think of it as basically an Ising model, right? So we're all hopefully familiar with Ising models, and so we have the energy of our Ising model, and it's given by the local fields on some spin variables that I'm going to call x, and then they're going to have local fields on another set of spin variables I'm going to call y, and then there's going to be some interaction term between these x spins and the y spins, right? So we can, and the connectivity graph of this model is going to look something like this. And so my X spins, they're going to be n of them. And so this is always, the number of these is always going to match, let's say, the number of qubits in my Hamiltonian. And then the number of Y spins is going to be little m. And the connectivity that I'm going to always have is this, all of the X spins are going to be connected to all of the Y spins, but there's not going to be any intracouplings between the X spins nor between the Y spins, right? So it's a bipartite graph. And now, we're going to allow ourselves to have, these local fields and these couplings be complex. So it's not really technically an Ising model, but this is a point that we'll get to in a moment why we do this. So you might ask, well, why restrict yourself to this particular kind of connectivity graph? And the reason we do this is because it then allows us to calculate the marginal distribution of the Gibbs state, right? So here you can think of, I've absorbed the temperature into, let's say, my local fields and couplings, and I can calculate the marginal distribution for the X variables by just summing or tracing out the Y variables. And you can do this analytically because of this, connectivity graph. Now, why do people care about RBMs? Well, why should you care about them? Well, it turns out they're universal approximators, which just means that, if you allow yourself to grow the number of these, what are called these hidden nodes or this hidden layer, if you allow yourself to grow the size of this layer, you're able to approximate any probability distribution on these variables, right? So in principle, it allows you to approximate any probability distribution, but of course, this may come at a cost of having, a large number of these hidden variables. Now, how are we going to use this to represent the quantum state? Well, what we're going to do is we're going to have our amplitudes of a given computational basis state be given by this marginal distribution. And because we want our amplitudes, or we want to allow our amplitudes to be complex, that's why we allow the parameters of our Ising models to be complex. Okay, so the key message here is that, right, when you define an RBM, and by that I mean you pick local fields and couplings, you've then defined a wave function, because for every possible computational basis state, you can plug that into this and output an amplitude. And so long as the number of parameters here, right, which is just n for the number of local fields on the, what we call the visible layer, m for the number of local fields on the hidden layer, and then the couplings, which are, there are n times m of them. So as long as this number is not exponentially large in n, you have an efficient representation. But now, okay, so let's say we now have a representation of our wave function in terms of an RBM. How do we actually train the RBM to, or update the RBM to approximate the ground state of the target Hamiltonian we care about, right? So our goal is to find parameters of our Ising model or of our RBM such that we've minimized the expectation value of our target Hamiltonian. Okay, so from now on, the target Hamiltonian will be denoted by h sub t. So, right, so what we want is a way to update our RBM or artificial neural network parameters such that we minimize this energy. But of course, we want to do this in the subspace spanned by our artificial neural network ansatz. And it turns out there's already an algorithm that does this, and it's called stochastic reconfiguration. And I won't go into the details of how you derive the equations for stochastic reconfiguration. You can either go to the original papers on this, or it's in the appendix of our paper. But at the end of the day, it turns out that it amounts to updating your RBM parameters using this equation. right? So this is like what the parameter was before the update. This is the new updated parameter, and you update it according to this, where S is basically, it's a covariance matrix that encodes the derivatives of your wave function with respect to the RBM parameters. F is basically a force vector. You can really think of it as a force vector because it's basically the derivative of this energy with respect to the RBM parameters. And so what this is doing is effectively doing a sort of a gradient descent. It's taking the derivative of the energy and it's pushing the parameters in the direction that lowers the energy. Now, this parameter gamma is in some sense controlling your step size, how far do you go when you update this parameter? And in the literature, it's called the learning rate, right? So, but this is just basically the step size you're doing in your optimization of these parameters. Now, the key here is that you need to calculate this covariance matrix S and the force vector in order to do these updates, right? So you need to have a way to calculate these expectation values that go into S and in F efficiently. And what we can do is we can calculate these using sort of the probability distribution that's defined by the artificial neural network. And the way we're going to do this is we don't want to sum over the all basis states because that's going to be exponentially costly. And so what we want to do is we want to approximate these expectation values using importance sampling. And the way we're going to do that is we're going to basically generate the samples using Markov chain Monte Carlo simulations, right? And the key is that we can do this with Markov chain Monte Carlo simulations that don't have a sign problem. And basically what we do is we pick basically a Metropolis Hastings acceptance probability that's basically the ratio of these probabilities. And because our ANN is like an RBM, so it's like an Ising model, calculating this ratio is very easy, or we can do it very efficiently when the spins are updated like one spin or k spins at a time. Now, this is sort of a detail for, let's say, the experts in the audience. You might ask, well, how do you pick this learning rate, the step size in your algorithm? And what you can do is you can interpret this stochastic reconfiguration equation as a dynamical equation. So you can think of the stochastic reconfiguration equation as like some discretization of a dynamical equation. So now I've kind of sort of promoted it to a dynamical equation. And then you can say, well, this is a dynamical equation that I can solve using my favorite integrator with an adaptive step size. So what people do in the literature, for example, is they use a second order Runge-Kutta integrator where you fix some error tolerance and then you're able to dynamically update the step size. Now, you might think that this is more costly because you have to basically calculate S and F multiple times in a single update of this integrator. But at least people have shown that using these adaptive step sizes actually end up getting you to the desired solution faster than if you hadn't. So it's actually a more efficient way of doing things. Okay, so let me now just take a step back and tell you, sort of remind you or do a quick recap of what the big picture is here, right? So the big picture is we're gonna use an RBM to represent our quantum state. We use Markov chain Monte Carlo simulations to basically get estimates of expectation values that we then use to calculate the matrix S and its inverse and the force vector that then updates the parameters. And then we just repeat this, right? Repeat this process until we've minimized our energy. So you might ask, how does this whole, methodology works? Or how well does it work? So, you can get state-of-the-art results for example, the J1, J2 model and the TJ model, which is a sort of a cousin of the Fermi-Hubbard model. So in, for example, these two papers, they actually solved the J1, J2 model like on a 36 by 36 lattice, and this TJ model on a 12 by 12 lattice. And as far as I know, the results they got were the sort of the best in class results. Now, that sounds great. But when you read, these papers more carefully, you learn that basically to get these results, they used 40 million heterogeneous cores, right? So they used a massive amount of classical computational power to generate these state-of-the-art results. And, so why is it so hard? Well, it turns out that, the energy landscape of these non-stochastic Hamiltonians in this artificial neural network picture, right, is rugged. And again, this may not be surprising, right? These are hard computational problems. So it's not surprising that the energy landscape is rugged and your training algorithm can get stuck in local minima. But, so when I see, a rugged energy landscape, I think of spin glasses and I think about, well, what are the techniques that we use when we study spin glasses to help us, explore this rugged energy landscape? And of course, the answer is parallel tempering. Okay, so let me try to give you sort of a big picture of how parallel tempering works if you're not familiar with it. So the idea is, instead of simulating a single system, what you do is you simulate multiple systems. And let's say you're doing a thermal parallel tempering simulation. What you would do is each one of these systems is assigned a different temperature. And you basically evolve each system initially independently from each other according to that temperature. And then at specified or pre-specified points, you allow these systems to basically swap configurations. So for example, here, the configuration or the system that was operating at temperature T1 gets swapped with the system that was operating at temperature T2. And now the system that's up here continues to be simulated with the temperature T2, whereas the system that was down here gets simulated now with the temperature T1. And again, these swaps are probabilistic. So sometimes, for example, like let's say here and here, the swap didn't happen. And then you continue evolving independently and until, again, at some pre-specified time, you allow the systems to swap, etc. Okay, and you can basically continue this, for as long as you want. Now you might ask, why does this method work? And one way to think of it is that, let's say the copies or the replicas of your system that are evolving at high temperature, they see a free energy landscape that's basically flat. So they're able to explore the landscape of configurations easily. Whereas let's say the replicas that are operating at very low temperatures are kind of stuck, let's say, in local minimum. And so when these swaps happen, basically the configurations at higher temperature are getting moved to the configuration, to the systems at lower temperature. And that sort of mimics getting kicked out of a local minimum. Okay, so it's this swapping from high temperature to low temperature that allows you to kind of get kicked out of local minima. And it turns out that in practice, people find that basically parallel tempering sort of far outperforms, let's say, an algorithm like simulated annealing. So because we're going to need it, let's sort of dig in a little bit into the details of how parallel tempering works. So, as I said, the first part of the algorithm is to just evolve the systems independently, right? So if you're simulating one replica at temperature T1, you just simulate it for some fixed number of steps. Same thing for the system at temperature T2. And then what you typically do, at least for the standard thermal parallel tempering, you want to use a swap rule that satisfies detailed balance. And so you can use, for example, a Metropolis-Hastings swap probability, which amounts to looking something like this, where it's the usual minimum of either 1 or the exponent of the difference of the energies of the two replicas times the difference in the inverse temperatures of the two replicas. So we want to use this as a kind of inspiration for how we're going to use parallel tempering in training our RBMs. And so this is what we're going to do. We're going to say that instead of having our RBMs operating, our different replicas operating at different temperatures, each replica is going to train according to this training function, Hamiltonian, sorry, which is going to be the training Hamiltonian minus a term that is what we're going to call a mixing Hamiltonian. And H0 is just, the energy, let's say it's just some relevant energy scale. You can pick it to be, let's say, the largest coupling strength in your, or the largest absolute magnitude of a coupling in your target Hamiltonian. It just sets some energy scale. And, the gamma is a parameter that basically sets the relative size of the training Hamiltonian to the mixing Hamiltonian in this Hamiltonian, or sorry, the relative scale of the target Hamiltonian to the mixing Hamiltonian in this training Hamiltonian. Sorry about that. Now you have a lot of freedom in what you pick for this mixing Hamiltonian, right? It could be something like the transverse field Hamiltonian. You can also pick something more phenomenological, like an entropy term, and then this would look more like a free energy term. And now we're going to treat this H0 times gamma as, the strength of the noise. So it's kind of like our temperature. And now we're just going to sort of adopt, the Metropolis-Hastings probability, even though there isn't really a notion of detailed balance in our system. And so we're just going to take the difference in the energies of the target Hamiltonian times the inverse, the difference of the inverse effective temperatures of our replicas. So this is how we're going to implement.
There seemed to be a question.
Oh, please. Sorry, I didn't see that Aaron had his hand up. Please go ahead, Aaron.
Hey, Tameem. So I just wanted to understand, backing up a couple slides, because I think I missed something. So you have this infrastructure for training an RBM using quantum Monte Carlo. You update this SR model, basically model parameters, until you minimize the energy. And you're now proposing using this parallel tempering model in the context of training that RBM to mimic these Fermi-Hubbard-like models. But is that correct? And I'm a little unsure exactly. Is it like in replacement of the quantum Monte Carlo, or where exactly are you proposing using this, and where was the breakdown exactly in the previous method in terms of the number of samples required to train it? Is it in the QMC samples, or that's where I had a question. Sorry.
Okay. Yeah. No. Absolutely. So in the standard approach right now, when you train these artificial neural networks, stochastic reconfiguration is kind of basically like gradient descent. It's a little more sophisticated than that, but that's basically what it is. And so, right, with any gradient descent algorithm, you can, and this is what happens, you can get stuck in local minima, right? And there's not really a mechanism to escape these local minima except to just, restart, right? So pick a new initial starting point for your training, apply stochastic reconfiguration, and see where it gets you. Now, what we're proposing is the following. So this is exactly where the picture that I wanted to get to. So on this picture, an update is exactly what I talked about initially, which is, you have your RBM or your artificial neural network. You do Markov chain Monte Carlo sampling to estimate the covariance matrix on the force vector, and then you update. So a single update along this line corresponds to, that whole process that I talked about. Now what we're going to do is we're going to put parallel tempering on top of that. So we're going to say that you update according to stochastic reconfiguration for a fixed number of updates. And each one of these, let's say RBMs, is being evolved or is being trained according to a training Hamiltonian that has this noise parameter gamma. right? So where this noise parameter gamma is the parameter here. And so we can have RBMs that are being trained with a very small gamma. So basically you're training them basically with the target Hamiltonian, but you can also have RBMs that are being trained with a very noisy or with a very high gamma. So it's like they're being trained with a high temperature or at high temperature. And then at specific points, right? So let's say after every 50 updates, you allow a parallel tempering swap move. And so you accept a swap move according to this probability. And then you just keep, yeah, go ahead.
So if I understand correctly, the original model was like a simulated annealing schedule, with the momentum being kind of the annealing schedule in some sense. And
you
now
can kind of think of it like that.
You're kind of replacing that with this more complex schedule.
That's right.
Okay. Thank you.
Oh, thank you. And Aaron basically set me up exactly for the next slide, which is you might think that, okay, this is all fine and good, but now it looks like you've increased the overhead of your simulation. Instead of simulating, a single training run, you're simulating multiple training runs. And are you actually going to benefit from this, right? And so the way we can sort of measure whether there's an advantage to using parallel tempering with n replicas as opposed to running n independent training simulations, right, without parallel tempering, is using the time to epsilon metric, which again is a metric that we're very familiar with in the quantum annealing community, right? But for those who are not familiar, right, this is basically a way to measure the computational cost of, let's say, finding or approximating the ground state to, let's say, a relative error of epsilon using U updates. So this is the formula, and let me just explain the various terms in this formula. So this term basically counts the number of independent repetitions of your algorithm that you need to do to guarantee that you achieve this success condition at least once if your single run success condition is this, or single run probability, single success probability is this. This is the cost of, use, let's say, the cost of performing a single update of the replica. And this is the most important factor. This is really our parallelization factor, right? So here, what we're saying is that suppose you're allowing yourself to do a simulation with at most n max replicas. Now you can have a choice. You could have a simulation where you just use one replica, which is like not doing parallel tempering, and then you can basically parallelize that over, let's say n max cores. Or you could run one parallel tempering simulation with n max replicas and basically parallelize those over the n max cores. So this is the sort of the parallelization factor that penalizes you if you use parallel tempering, but doesn't if you don't. And basically the key is, will the improvement in the success probability because of parallel tempering, outperform this factor, right? And only then will you actually have an advantage to using parallel tempering. So how are we going to benchmark this approach? So again, we're using inspiration from from quantum annealing, and we're going to look at this problem that's very famous in quantum annealing, which is the precipice problem. And so our target Hamiltonian is going to be this transverse field term plus this classical cost function, where we've picked the classical function to look like this. It's a permutation-invariant cost function, so it only depends on the Hamming weight of the bit string. The global minimum happens at Hamming weight n, and it takes value -1. And everywhere else, basically, the cost function is linear in the Hamming weight. So why is this a deceptively hard problem for heuristic algorithms? basically when you randomly start from a bit string, you start somewhere in the middle here, and your heuristic local algorithm will just kind of follow the gradient down and get stuck in this false minimum. And once you're here, you need to basically make n steps upwards to go and find this global minimum. And as n gets larger, this becomes more and more unlikely, and it actually becomes exponentially unlikely. So this is a sort of artificially hard algorithm, even though it's quite simple in some sense because it's permutationally invariant. So we're going to even make the problem a little simpler, and that is we're even going to sort of encode the permutation symmetry into our RBM, right? So one way to do that is to basically make sure that the amplitudes of your wave function only depend on the Hamming weight or on the sum of x. And so basically what that means is that on your visible layer, all the local fields have to be the same, and all the couplings have to not depend on the index I. So you can just basically pull it out. And this is a simplification because it means that our RBM can be parameterized with basically 2m plus 1 parameters. So let's see how parallel tempering and not parallel tempering do on this problem. So here I plot basically the probability of finding the ground state as a function of the number of updates for the case with no parallel tempering and the case with parallel tempering. And I want you to notice that basically the color coding on the two plots is different. And what you should see is that basically for the case of no parallel tempering, by the time you get to the precipice problem with n equals 10, basically the probability of finding the ground state is 0. Whereas you see with the case with parallel tempering, you can go up to n equals 16 and you still have a pretty high probability of finding the ground state. Okay, so already, at least just looking at the ground state, the probability of finding the ground state to some relative error epsilon, there seems to be a clear advantage to parallel tempering. But again, right, the way to properly do this is to calculate the time to epsilon. But before oh, please go ahead.
Hi, this is Hidetoshi.
Hi, Hidetoshi.
Well, you use the transverse field driver in this case, and I wonder how do you implement this quantum-like term in your classical simulation?
Good. So in the classical simulation, all you need to do is to calculate the expectation value of the Hamiltonian. And basically what happens is you can calculate this efficiently for the transverse field because it basically maps a classical spin configuration to a classical spin configuration with Hamming weight 1 or Hamming distance 1 away. And so these overlaps, you can calculate them, and you can calculate them sort of efficiently. And you estimate the expectation values. Again, you can do it using importance sampling.
So you use a transverse field term as a driver to move a state to another state with Hamming distance 1.
Oh no. Okay, sorry. Sorry. So the transverse field driver here is being used in a sort of similar way as we do in quantum annealing. It's sort of the source of the noise, right? And so because we want to use sort of parallel tempering, we need a source of noise, right? We need a sort of a high temperature sort of system and a low temperature system. For the low temperature system, and let's say the 0 temperature system, we're using the target Hamiltonian for the training. For the high temperature system, it's basically the target Hamiltonian plus a very, very strong transverse field. So one way you can think of it is that basically at high temperature, quote unquote, the ground state is the uniform superposition state. At low temperature, the ground state is the ground state of the target system. And what we're doing is we're doing, in some sense, quantum parallel tempering, where we're allowing sort of the energy landscape to change as we tune the strength of the transverse field. Does that help?
Well, vaguely, I understand that. Well, you use the metropolis update rule, which involves just the classical energy difference and the temperature or parameter difference. But you use the transverse field term, which is not classical energy term.
That's right.
Well,
so okay, good. So the way you calculate that energy is exactly the same way we calculate that energy, let's say in quantum Monte Carlo. You know, that expectation value, you can write it as basically an expectation, or yeah, you can write the the expectation value with respect to the quantum state in terms of, you know, a sum of the classical configurations.
Okay, you use the expectation value, not the, okay.
Yeah.
Or given value of gamma.
That's right.
Okay.
Yeah.
I think I understand. Okay, please go ahead.
Let's see. Good. So let me just show you actually how the parallel tempering is actually working in these simulations. So here on the left plot, I show the average energy as a function of the updates, and I do it for the lowest two, or the simulations with the lowest two noise, right? So basically, this gamma 1 is actually 0, and this gamma 2 is the one right above it. And let's not worry about this plot for a moment. Let's just look at this plot. And what you see happens is that very quickly, the simulation basically, both replicas at these two sort of, let's say, temperature scales, basically saturates for a long period of time. And it turns out that this energy is actually the first excited state energy. So in both replicas, the systems converge very quickly to the first excited state energy. And it takes a very, very long time until the low noise replica finds the ground state energy. So this is actually, turns out, the ground state energy. So what's happening here? So to show what's happening here, we can sort of look at what the swaps that are happening. And so here I plot the original index of the replica as a function of the number of updates. And again, for the zero noise and the one noise above it. And ignoring this kind of initial craziness, what you find is that, for this particular realization of the experiment, the replica that was originally at zero noise is the configuration that's at zero noise for all this period, whereas the configuration that's at the one above noise is swapping with with the other replicas. So it's the original index 2, then 1, then here it's jumping to 9, it's back to 2, 9, 8, etc. Until this event here, which notice is exactly this point here. The configuration at the higher energy or the higher temperature is being swapped with the zero temperature case. And this is what causes the zero temperature case to find the ground state. So the fact that we're doing this kind of traversal in higher temperature, higher noise replicas helps us get out of the local minima that we're stuck in here to get to the global minima, right? Which is exactly what we wanted our parallel tempering sort of to do. So now, as promised, let's look at this for the time to epsilon, right? So here I show, this is the case where I use at most 40 replicas for parallel tempering. The blue curve is the case without parallel tempering. So it's like having a single replica, and then we have 10, 20, and 40 replicas. Now, what you should see is that basically at n equals 9, you're already seeing an advantage for using parallel tempering over no parallel tempering. And basically, at n equals 11, the cost is so high that I basically stopped doing simulations to try to get an estimate of the probability. So very quickly, we see that parallel tempering is advantageous. You might wonder, what's going on, here? Why is why do the curves kind of hug each other? I think this is basically an artifact of the fact that we didn't optimize the distribution of gamma values. So if you like, of our, the strength of the noise. And, if we optimize that, I think we would see a separation of the curves. And on top of that, I think we would see even better performance if we optimize the distribution of noise. And that's actually what we're currently doing. Okay, so in my last couple of minutes, let me just say that you might say, well, this precipice problem is kind of artificial. Will this work for more realistic problems? So, right, my collaborators at Sandia are quantum chemists, and so they wanted us to sort of look at sort of molecular problems. And so one problem that's kind of easy to study is this 4 hydrogens arranged in a rectangle. Where you can pick the distance of the hydrogen atoms from the center and the angle that they make. And we picked some numbers that we found in the literature, right? So there's you pick the radius to be this 1.8 angstroms. The reason you pick it is because these methods from quantum chemistry seem to struggle at this radius. You have to pick, with these molecular systems, you have to pick some basis set. And that gives you a second quantized fermionic Hamiltonian. And then we use Jordan-Wigner to map that Hamiltonian to a qubit Hamiltonian. And for this problem, it's an 8-qubit Hamiltonian, which is kind of just nice because we can, do a lot of numerical simulations with 8 qubits. So what do the results, before I talk about the results, now there's a slight sort of technicality here, which is that the fermionic Hamiltonian is actually electron number conserving, and the ground state has 4 electrons in it. And when you do the Jordan-Wigner mapping, that means that the ground state of the qubit system only has weight on Hamming weight 4 computational basis states. And so you can have a choice in the sense that you can sort of choose, if you knew this ahead of time, you could restrict your RBM to only sample from Hamming weight 4 states. And in that case, we chose to use a mixer Hamiltonian that basically preserves the Hamming weight. Or let's say if you didn't know that ahead of time, you would want to sample the entire set of, or allow yourself to sample all computational basis states. And so we picked sort of a mixer Hamiltonian that was basically the transverse field. So what do the results look like? So again, we see that parallel tempering basically works better for almost all the angles. For when you restrict the Hamming weight, you don't get an advantage at theta equals 90, but that's the most symmetric case, right? So that's when the rectangle is actually a square. But for the other, at least 2 angles that we studied, parallel tempering gives an advantage. And in the case where you don't restrict your sampling to the subspace of Hamming weight 4 states, you actually always get an advantage for parallel tempering. So with that, let me conclude, right? So basically, for me, this was a project I really enjoyed because basically I used all of this sort of experience techniques that I learned, studying quantum annealing, adiabatic quantum computing, to kind of develop, let's say, a quantum-inspired heuristic algorithm for training these ANNs to approximate ground states of quantum Hamiltonians. All the work that we did in the paper and that I presented today, right, we use RBMs and stochastic reconfiguration, but this parallel tempering doesn't require you to use those, right? It would work with any ANN you chose and any sort of update scheme you chose for that ANN. So I think it's sort of very flexible. And really our ultimate goal here is really to develop sort of a very flexible tool to use to tackle ground state approximation problems, and in such a way that we can really use this to benchmark quantum computers, right? In the sense that we want to have a sort of state-of-the-art classical algorithm that pushes the boundary as much as possible, such that when a quantum computer can beat it, we really can say, okay, the quantum computer has really now done something that we just could not do classically. And with that, I will stop here and maybe again put up the advertisement for AQC, and I'll take any questions you might have.
Thank you, Tameem. Yeah, there's a question.
Go ahead,
Thank you,
Aaron.
Tameem. Yeah. So my question is, after doing this, like where are the tall poles now in terms of the bottlenecks for training the model? Like, and the second is, I guess there's the training, but there's also kind of like, I guess there's also like an inference in terms of like being able to perform a quantum simulation now with the RBM, I guess, right? And I'm a bit confused as to where the tall poles are. Is it still in the training of the model? Is it still complicated to perform inference? And where are the computational bottlenecks now classically? Is it in the Monte Carlo? Is it in parallel tempering? Like, I'd like to understand that a little better.
Okay, good. So the bottlenecks, I believe, are still, okay, so, that rugged energy landscape that people talk about when using artificial neural networks to study the ground state problem, the hardest part, it turns out, for your artificial neural network to learn is the relative phases of your ground state. That turns out to be the hardest part. And those basically cause this rugged energy landscape as a function of the parameters of your artificial neural network, right? This remains the bottleneck, right? And it's in some sense, it's the usual one for hard optimization problems. Now, what does this rugged energy landscape depend on? It depends on, for example, if you chose something other than an RBM, right? So for example, if you chose a CNN or, a group CNN, that your choice of architecture changes the energy landscape. So some artificial neural networks work better than others, depending on the Hamiltonian you're interested in. What some people do, and this turns out, can result in dramatic improvements, is if for some reason ahead of time what the relative, or like you have a sort of an inkling of what the relative phases of the ground state need to be, and if you hard code that in a sense in your artificial neural network, that also can make the training easier. All right. So in some sense, we haven't completely escaped, the hardness of these problems, which we know comes from, in some sense, a kind of frustration, right? And what's nice here is that at least we've avoided, we've sort of the hardness of classical methods, and you can say you've just moved it to somewhere else, right? So the hardness that we had for quantum Monte Carlo, or the hardness that we had for tensor networks, you just kind of moved it somewhere else, and I would say that's perfectly reasonable. But again, what's nice about, I think, artificial neural networks is that it's an active area of research. It's people have developed algorithms that are very parallelizable, so you can sort of put them on HPCs very easily. And I think sort of bringing in or developing new methods using them is interesting. So
yeah, no, I'm a big fan of them. I guess my question is like, I guess so both in the training and the inference, you're going to need to perform this procedure to be able to simulate a Fermi-Hubbard model, basically, using the RBM. You still will need to do the full procedure that you had mapped out, not just in the training, but kind of in the inference / simulation phase of the model itself. Is that right? Like or are you
so you would definitely
ground state energies of the Fermi-Hubbard model, which is corresponding to some evaluation of the RBM at a given configuration? I got lost a little bit in that.
Okay, so definitely this. So in order to estimate S and F, you basically need to do a Monte Carlo simulation, and it's true that basically if you need very, very accurate estimates of, let's say, the force vector and the covariance matrix, that means you need a lot of samples, and that can be costly. And what can be even worse is you might say, maybe the the RBM or the ANN is kind of like a spin glass, and so you actually need, you need high quality samples, and to get high quality samples may take exponential time. So just this step in principle could be costly, right? And just to estimate the force vector and the covariance matrix, to just update the parameters once. Now, what people do here is basically they parallelize this Monte Carlo sampling across, let's say you do it across 40 GPUs, and you can sort of get a lot of samples, hopefully very quickly, to get these estimates. So that's one sort of computational cost. But then you have to do these this is just one step in the update, and you might need to do many steps until your ANN converges to the minimum that it wants to. So, the number of updates could be very large. The cost of a single update could be very large. And basically, our hope is that basically by allowing these parallel tempering moves, you at least allow yourself to get out of local minima.
Thank you.